Welcome back, and let's start looking at some of the mathematical relationships associated with equilibrium now that we've kind of got the ideas of what it means for a system to be at equilibrium bedded down. Just going back to our assessment statements from the IBO, okay, which we should always be referring to. We're now in the realm of looking at this system here, where the equilibrium law describes how the equilibrium constant Kc can be determined for a particular chemical reaction, talking about the magnitude of the equilibrium constant equaling the extent of a reaction, and then also looking at the reaction quotient and what that means for Kc. You'll also notice that in this case, we've got some applications and skills now. So we need to be able to deduce the equilibrium constant for an expression, aka write the expression and substitute in some values and solve for it. And you'll notice that this stipulates for a homogeneous reaction. So this is like what we've talked about in the past. All the reactants and the products would be in the same state. Okay, and then the relationship between different equilibrium constants for the same reaction, the same temperature. So this is looking at the ways that we can manipulate the maths in terms of Kc. So just a quick reminder, when we're talking about equilibrium, we're talking about dynamic equilibrium. So this is to say that the reaction is still occurring in both the forward and the reverse directions. It has no observable change to concentration at the macro level. With an open system, energy and matter can transfer between the surroundings and the system, and when the system is closed, it's only energy that can transfer between the system and surroundings. And that a reversible reaction is one where the products can react to reform the reactants, and when we have a reversible reaction, we're always using our double-headed arrow, which is the Le Chatelier's arrow. Okay, so this is just a quick note on homogeneous and heterogeneous. Okay, homogeneous, much like any time we talk about homogeneous systems, we're talking about things all being the same. So in the case of homogeneous equilibrium, this is a reaction system like the nitrogen-oxygen forming nitrous oxide system that we have over here, where we can see that all the reactants and the products in the gaseous state. Heterogeneous equilibrium, in the other hand, is one where we have reactants and products in mixtures of states. So like this iron rusting, this redox reaction here where we have the rusting of iron, we have this iron reacting with water and forming Fe3O4 solid. We have mixtures of solids and gases, so this would be heterogeneous. So when we're talking about equilibrium, we want to talk about the extent of reaction. So to the extent or to the limit to which the reaction will proceed in the forward direction. Okay, so essentially when we talk about extent, we're always talking about how much the forward reaction is going, and it gives us a ratio of the concentration of the reactants and products at that point where equilibrium is reached. Okay, so for this, the extent of reaction determines how much product will be formed when a system reaches equilibrium. And we've talked about how this is important to industry, because if you want to be making a pharmaceutical product, or if you want to be making something that's sold industrially, you need to know how much yield you're going to get, and you want to maximize that yield as much as possible. Rate of reaction is going back to kinetics, and we're talking about the change in concentration of reactants with time, always over a time interval, and this always determines essentially how quickly the reaction will proceed, not how far. So the idea of the rate of reaction and kinetics can give us an idea of how quickly the reaction will proceed. Equilibrium tells us, though, how far it will go, so it allows us to determine how much product we can expect to get from a particular system. We've looked at the Haber process, so I'll go through this pretty quickly. But essentially, if we look at this here, we can see that there appears to be no fixed relationship between the concentrations of nitrogen, hydrogen, or ammonia as the reaction proceeds by changing concentration. However, we do start to see a relationship happening if we rearrange this equation and take these concentrations and start to treat them mathematically. So you can see here that in this one here, what we've started to do is now take the products and divide them by the reactants. We see that some of these then are coming into line, and they're very similar. Okay, for different equilibrium mixtures. However, when we actually take them to the power of their coefficients, we actually see this interesting thing here where it starts to become a constant value. And this is what we define as our equilibrium constant. This ratio of the products raised to the power of their coefficient divided by the reactants raised to the power of their coefficients is what gives us our Kc value. Okay, so essentially the last column is representing the concentration fraction. If we take this at any point that isn't equilibrium, it's known as Qc. It's exactly the same mathematical formula for Kc, it's just that the values that we substitute in didn't happen to be equilibrium concentration values. Okay, so it becomes the equilibrium constant Kc when we measure those values at a given temperature. So the equilibrium constant is Kc, and we use this expression here. When you're doing these kinds of questions, you always want to make sure that you write your equilibrium expression. There's usually a mark always attributed to writing the equilibrium expression and then substituting in and solving for your values from there. Okay, so if we look at this, we can see that it tells us that the equilibrium constant for the Haber process at 400 degrees C is 0.052 m to the negative 2. Okay, so this is telling us that at this temperature, this is a measure of the ratio between the products and the reactants. This is the general form of our equilibrium law, okay, and so we can see that Kc is equal to our products P and Q raised to their coefficients divided by their reactants. You should be pretty confident with this. It is just simply taking the information given in our equation, always making sure that our chemical equation is balanced, of course, or our coefficients won't be right, and then forming our expression. So this picture, hopefully you've already seen if you've done your pre-reading, but it is breaking down our overall expression. K is simply the symbol for the constant. We change the subscript because it indicates what we're basing it off. So Kc is the equilibrium constant based off concentration values. Okay, the terms are always multiplied, not added, and the exponents are the coefficients used in our equation, and of course the square brackets means mole per decimeter cubed, which is the concentration, and for it to be Kc, not Qc, these must be measured at equilibrium. So if we take this and we work it out when it's not at equilibrium, what we end up with is this Kc value. So we can compare this to literature Kcs to QCs at particular times and determine what will happen for our reaction to reach equilibrium. So if we calculate Q and compare to a known value of K for that reaction at a given temperature, we can work out whether or not the reaction has gone as far as it would or what's going on. So if Q is greater than Kc, then the reaction is going to proceed in favor of the reactants because we need to make it smaller. If Q is less than Kc, then it'll move to the direction of the products to make Q bigger. And if they're equal, then the system must be at equilibrium. And we can see this graphically by this diagram here. So if Kc is smaller than Qc, Qc will move in the forward direction, producing more products to make it equal and drive the system towards equilibrium. If Qc is bigger than Kc, then the reaction must proceed in the reverse direction in order to increase the amount of reactants and bring it back in line with Kc for the system to reach equilibrium. Okay, let's have a look at this in terms of a question. So we are told that the equilibrium constant for the reaction, so that's going to be Kc, and then we're given the reaction, and these arrows indicate that it's at equilibrium, is 4.5 molar at 80 degrees C. The gas mixture in a 2-litre vessel at 80 degrees C contains 0.2 mole of N2O4 and 0.3 mole of NO2. Decide if the reaction is equilibrium, and if it is not, predict the direction the reaction will shift to reach equilibrium. Okay, first up we're going to have to write our expression. So we're going to write our Kc expression is going to be our product, so the concentration of NO2 raised to the power of our coefficient, which is 2, divided by the concentration of N2O4. Okay, so now, sorry, we should probably, because we don't know if it's Kc yet, we'll call it Qc. We're going to find the reaction quotient. Okay, so now we're just going to substitute in. And when we substitute in, we'll take our values. So NO2, okay, remembering that this is a 2-liter vessel. Okay, so if it was 0.3 mole of NO2 in 2 liters, that is going to be 0.15 molar concentration. Okay, and that's going to be squared, all divided by, we had 0.2 in 2 liters becomes 0.1. Okay, so if we have a look at how that looks, without me writing it all out, and we can see that we've worked out the concentration, so this is dividing by 2 to find the overall number of mole, or the molar concentration here, and we get 0.23. Okay, so we're asked to figure out what the direction is. We're told that it's 4.5 at 80 degrees C. We're at 0.23, so 4.5 is much greater than that, so the reaction must proceed in the net forward direction in order for it to reach equilibrium, because 0.23 is much smaller than 0.45, than 4.5. So in order for us to make that number bigger, we need to increase the size of our numerator, which means we're going to favor the formation of products. Okay, so that should set you up to be able to do a couple of these practice questions yourself and determine whether or not a system is in equilibrium and predict what direction it has to go. Good luck, and we'll go through the answers when we get back to class.